By the end of this session, you'll know this information about gravitational fields. You'll know the force of attraction between two masses can be found by using Newton's law of gravitation, which is F equals minus big G, m1, m2, all divided by r squared. You'll be able to use Newton's law to calculate the force on a mass and show your results on a plotted and sketched graph. And you'll understand the importance of the negative sign in the formula. You'll also know this about electric fields. You'll know the force of attraction between two charged points can be found using Coulomb's law. F equals K, Q1, Q2, all over r squared. You'll be able to use Coulomb's law to calculate the force on a charged particle and show your results again on a plotted and sketched graph. And you'll understand the sign convention adopted for each charge. It will soon become clear to you that gravitational and electric fields have a great deal in common. In order to demonstrate these similarities to you effectively, we'll use this slide template whenever gravitational and electric fields are closely related. Gravitational field information and demonstrations shall always be on the left-hand side, and electric fields shall always be on the right-hand side. Gravity is an attractive force between any objects with mass. Newton understood that the force of gravity is what made apples fall towards Earth and planets orbit the Sun. Newton's law of gravity describes the force of attraction between two objects with masses m1 and m2, which are separated by a distance r. In order to investigate this relationship fully, we need to introduce our gravity guide, Mike the Mass. Hi, Mike.
Hi there, I'm Mike. I have a mass of 1 kilogram and I float around in space where the force of gravity is very small, but not zero. When I float anywhere near a planet, I feel immediately attracted to it. Hey, good looking, what you doing tonight? Newton's law of gravity helps me to calculate the force of this attraction that I feel for the planet and that the planet feels for me. Let's imagine that I'm floating somewhere near your planet Earth. In order for me to calculate the force of attraction between us, I need to know the mass of the Earth, m1, which is 6 times 10 to the 24 kilograms, my mass, which is a tiny bit smaller at 1 kilogram, and the distance I am from the centre of the Earth. It's about 100,000 kilometres, or 1 times 10 to the 8 metres. I also need to use something scary sounding called the universal gravitational constant. It isn't anything big and impressive to be put off by. It's just a number that never changes. That's why it's a constant. It's sometimes called big G. And G is 6.67 times 10 to the minus 11 Newton meters per kilogram squared. So, the attractive force F between me and the planet is found by putting these values into Newton's equation, just like this. We find that the force between me and your planet is 0.04 newtons, and that's negative. Force is measured in newtons, of course, you know. But why, I hear you cry, is the force negative? Aren't we attracted? Well, it has to be negative because, as you can see, the attraction I feel for the Earth and the distance I am from the centre of the Earth are in opposite directions. And since force is a vector quantity, this difference in direction has to be taken into account. The negative is very, very important, as you will see later on. Attractive forces are always negative.
Thanks for that, Mike. Okay. Electric fields, unlike gravitational fields, can either be attractive, like between two unlike charges, or repulsive, like between two like charges. The force that exists between two charged objects is called the electrostatic force. We can work out the magnitude of this force using Coulomb's law, as long as we know the size of both charges, Q1 and Q2, and the distance they are separated by, r. In order to investigate this relationship fully, we need to meet our electrostatic guide, and I'm sure you're all looking forward to this. Here's Claire the charge. Hi, Claire.
Hi, I'm Claire. I have a charge of +1 coulomb. See? Since I am positively charged, I feel myself attracted to negatively charged objects and repelled from positively charged objects. I float about in the vacuum of space, interacting with electric fields that come from all charged objects. Hey, look! Here comes a proton, way over there in the distance, about 100 meters away. Cooey! Let's work out the electrostatic force between us. We're going to use Coulomb's law to calculate the magnitude of the force. I also need a value for K to complete the calculation. K is a constant again, just like big G in gravitational fields, which is calculated using the formula 1 over 4 pi epsilon naught. This is not as scary as it looks initially. The first part, 1 over 4 pi, simply relates to the amount of electric field radiating in all 3 dimensions from the point charges interacting with the other charge. The second part, epsilon naught, denotes something called the permittivity of free space, which is basically how hard or how easy it is for an electric field to propagate through a vacuum. The constant, epsilon naught, is 8.854 times 10 to the minus 12 farads per meter. So using Coulomb's law, the force between me and the proton is 1.43 times 10 to the minus 13 newtons. The answer is positive, so we are repelled from each other. Why don't you repeat this question, but instead of using a proton, use an electron, which is charged minus 1.6 times 10 to the minus 19 coulombs. I think you'll find I'm attracted to them.
But not as much as I'm attracted to you, Claire. It's time for you to demonstrate your understanding so far and to attempt the 2 questions on the screen. If you are unsure about how to do these questions, then feel free to click back a couple of slides and remind yourself how to do the calculations. After you've found the answers, you should plot your results on a graph, 1 graph for each field, and you can check your answers on the next slide.